Our next speaker is Kimberly Prather. She's professor of chemistry and biochemistry at the University of California, San Diego. Her title is New Insights into the Role of Aerosols in Climate Change. Do you want to do this, perhaps? Because we lost you a little bit.
I'm going to put it. So I just clip it on this thing. I just stick it on there.
Okay, well, good morning, everyone, and it's a great honor to be here, and I'd like to thank Mark and the Dreyfus Foundation for the invitation to come and tell you a little bit about our research that we're doing, and I will be touching, Jim did a great intro for a lot of the things that I will be touching on as far as climate change. In particular, when Mark first invited me, he said, make this really basic. A lot of people in the audience won't even know what an aerosol is. There's a chance, so step back. So I'm going to do that. But then I was at the annual Aerosol meeting was this week down in Florida, and there's a number of people here that are from that community. So I'm sort of trying to span the range from the very basic sort of background on aerosols all the way through to the impacts and some of the newer research we've been doing. So with that in mind, the research in my group at UC San Diego focuses on atmospheric aerosols. As people know, it's a major component of air pollution. It's been a relatively understudied component of air pollution until the last decade or so. Similarly, basically when you hear about air pollution, for years we heard about ozone. We worried about respiratory effects from ozone and pollutants in the atmosphere. It was only within, as I say, about the last decade or so that people started really drawing attention to aerosols. There's plots for the worldwide that show that as aerosols increase in the atmosphere, there are deleterious health effects that go far beyond just respiratory, but they go beyond respiratory issues all the way, extending to premature death. And that's a hard one to sort of quantify, but basically aerosols are very, very effective transport mechanisms to get pollutants and toxins into very deep regions of our body that they just wouldn't get otherwise. And so that's kind of where I started. I started out looking at air pollution. I was very interested in sort of the aerosol component, which is the relatively messy side of air pollution, but a very important side of air pollution nonetheless. The examples we see every day, dust, soot, sea spray, bacteria, viruses, pollen, all of those qualify as aerosols. The environmental impacts, as I mentioned, human health is a major target, but also the climate aspect, which is what I'm going to focus on today. Visibility just tells us through there. When you see poor visibility, it's the aerosols that are doing it. Land and ocean fertilization, both from the good side as far as leading to ocean productivity, as well as land fertilization, but also some of the negative sides, such as acid rain and other things can happen as well. So today I'm going to kick off with just sort of a little bit of background on atmospheric aerosols, breaking them down into sort of the direct and indirect effect that Jim just alluded to. I will sort of finish up with talking about what our approach has been. When I came into doing this type of research, there was a pretty big gap. I came in from the chemistry side. I was trained as a fundamental physical chemist who studied gas phase reaction dynamics. And there was just a pretty big gap as far as our chemical understanding of what these aerosols were doing in the atmosphere. And so that, I brought in sort of a different perspective of, how important chemistry might be on this problem. To be honest, I've been shocked at how sort of there's been a certain resistance for a long time as far as how is the chemistry really important. We still have battles over whether we even need chemistry to explain what's happening in the atmosphere. So those are turning into less and less battles, but still, they're there nonetheless. So the approach that we use in my group, is this guy working? Kind of. He's a little wimpy one. But anyway, the approach that we use in my group is a dual-pronged approach. Truthfully, when we started out developing the instruments that we developed, I planned on doing lab studies. I had no field experience. I didn't even know what a field study was. But then in the end, once we had the instrument working, we decided to sort of sniff the outside air and see what we saw. Early funding was very difficult to come by. People thought, no way will this instrument ever tell you anything about sort of what's going on in the complex world. So we decided to take a peek at the atmosphere, see what was going on, and then use that to drive the lab studies that we do. It's turned out to be a really nice approach because, when you go to the lab and you're looking at these complex systems, there's so many choices of things you could study. And to me, personally, and also for my students, it's more fun to study things that have very direct relevance. And we're at that point now. And so we jump back and forth, as I will show you today, and I hope you'll get a flavor of the kind of approach we take between lab and field studies, as do more and more people. We always keep in sight the models. The models are the key tools to predicting where things are heading. As Jim talked about, we're trying to understand how much warmer it's going to be. What are the changes going to be by the end of the century? There's a lot of uncertainty in that. A lot of the reason for that is because the models, as far as the chemistry goes, are pretty cryptic. I mean, they're because it's hard. It's hard to model all of the processes that go on. And so we're trying to slowly feed sort of some of the bigger effects into these models and see how much of a difference it makes, particularly with respect to the aerosols. Another side of things that we look at is the sources. One of the things that we've been able to do, basic research in our group, we measure the chemistry of individual particles one at a time. And we measure thousands, millions, billions of these particles all over the globe. And one of the big questions we ask repeatedly is, where did these particles come from? Why are they there? And the reason we do that is we're always thinking down the road to the policy. I have to think about it. There's a lot of reasons you might ask questions, but I think in the role that we have right now, we need to be feeding into the proper policies being established, and we can only do that. One of the best ways, I think, to do that is to actually figure out where things are coming from. The regulators are much happier when you actually can tell them, if you remove this particular source, things will change by this amount. So that's how we think about things. So the final part of the talk, I'll just basically focus on two examples of some of the newer research we've been doing. So stepping back to sort of the basic sources of aerosol particles, I think everybody in this audience is very familiar with them. As I say, they're very visual, so it's easy to see that they're there. The part I like, as I mentioned, is that we study single particles one at a time, and they're beautifully, I think, complex. I noticed wallpaper in the other room had some cool images of particles, too. I think they were. They all little round things look like particles to me. But basically, the range of complexity spans, these are actually from the ocean. There's just a wide range of particles. And when you just look at the images, which is really the main information we had when we got started, we're looking under a microscope and looking down at these, you can see this complexity. But the sort of the downside of the drawback to doing this approach is that it's slow. You're looking at 10 particles and trying to extrapolate to the atmosphere. So the goal with our research has been to look at a lot more particles as fast as we can, never sample things onto filter paper, and to try and sort of go after things in a more real-time approach, more in line with what people have been using for gas phase analysis for years in atmospheric chemistry. Another thing to keep in mind about aerosols and pollution in general, and I think this has been a great graph that maybe some of you have already seen before. Basically, one of the things that people used to think was, if the pollution is bad, like if it's really high and it's increasing in China, that's China's problem. If our pollution's increasing, that's our problem. Mexico City's is going up, that's their problem. But what's been shown recently is that the atmosphere has no walls. Air pollution is transported globally. We get a lot of our pollution from Asia and the United States. A lot of that is in the form of dust, which is one of my favorite things to study. Dust, I'll come back to. We import a lot of our pollution, and we also we export a lot of our pollution over to Europe. And there's millions of examples of sort of this airflow and basically air pollution being transported from one region to another. So I think this has really shown this international sort of global problem in that we have to work together. There's no more finger pointing. We need to work together to actually establish the problems and figure out ways to solve them. So just a basic sort of tutorial. Jim focused on CO2. Again, that is the main thing that's been studied, and I think obviously we need to keep focusing on the CO2. But the scary part to me, at least about the aerosol side of things, is how poor our understanding is of the aerosol component. I think before we can make any major changes, adding more aerosols to keep things cooler or whatever people keep talking about, we need to establish a much better understanding. So the way aerosols work, Jim mentioned the solar coming in. Aerosols can actually absorb the incoming radiation, which leads to warming. By doing that, they block a lot of the light that's coming down to the surface. They also reflect the light back into space. And so if you don't get the light down to the surface of the Earth, then you aren't going to get the emission of infrared, and you will not get the noted greenhouse effect. So the aerosols are basically acting in a way to sort of shield us. And so a lot of people say, air pollution is a good thing because it's cooling things. And I would have some debate about that, and we'll talk more about that. But basically, this is what's termed the direct effect. The indirect effect has been termed our largest uncertainty in climate change. And basically, at the center of every cloud drop is a particle. And only certain particles form clouds very effectively. We're still trying to sort out what determines whether a cloud forms or not. And so clouds cover roughly 60% of the surface of the Earth. We don't completely understand why they're there or why they're not. In some places, we're starting to see major effects where people are starting to pinpoint aerosols as being important in affecting meteorology and weather patterns. They've been shown in this case, if you have a lot of extra pollution in a cloud, you only have so much water, and so you form smaller drops that can never grow big enough to rain, and so you have much longer lived clouds, which leads to more cooling, but it also leads to suppression of rain and drought. So now aerosols are being linked, or air pollution in general is being linked to potential problems with our water supply, which is significant. These are just two images of a cloud drop in the liquid phase versus the ice phase. We've been looking at sort of the differences in the chemistry or the cores of the particles that form these two. Ice phase is very, very difficult to study because their concentrations are so low. So we've been focusing on those in particular. All right. So just to step back, Jim mentioned the IPCC report. This is the fourth IPCC report that he mentioned came out in 2007. Just a few take-homes in this. Basically, if you look at the greenhouse gases, which are on the top, you can see that they're noted warming. Our uncertainties are relatively small. But if you come down to this green box, this is where the aerosols fall. And what I want to draw your attention to is how large sort of these uncertainties are. In fact, if you go from the size of these uncertainties down to sort of our total, sort of net uncertainties for human activities impacting climate, the size of the error bars, or not error bars, but uncertainties are rather large. And so the goal of our research and a lot of other people's research, it's really ramping up now, is to try and gain insight to why these error bars are so large and try and help reduce them so that we can sort of get a better handle on where are we going? Where is the temperature going to be at the end of this century? So stepping back a little bit further, this was the third IPCC, and I like this figure still because it focuses in on a topic that's near and dear to my heart, which is aerosol mixing state. And by aerosol mixing state, what I mean by that is the chemical associations. Which chemical species are associated with which other chemical species in the same particles? Because ultimately, that is what affects or impacts the climate properties of aerosols. And so if you look at sort of the aerosol region, you can see here it's basically our understanding is very low. The point I want to make is sort of these different categories of what I would call mixing state. Basically, you can break the aerosol down into the different types of particles that are floating around sort of individually in the atmosphere. And what you see is what I want you to see is sort of the labels that are used right now. And basically what we think about are sort of the basic things that are emitted. We've got a sulfate. One of the key things I want to draw your attention to is sulfate versus black carbon or soot. They're in separate categories. We look at sulfate as being very reflective, very cooling. We look at soot as being very warming. But one of the things I want to point out is if you actually measure these particles one at a time in the atmosphere, are these really separate? That's really, really important, and I'll come back to this. I'll tell you the punchline is no. Most of the time, no. And so we're never going to get the right answer as far as how the aerosols are influencing climate until we get these particular categories correct. The other thing that I want to point out is mineral dust. Now it actually has in the fourth IPCC a little bit of a value associated with it as far as, I believe it comes out as cooling. But basically, you can see mineral dust is the least understood as far as impact on climate. So basically, why are these uncertainties for aerosols so large? The biggest reason is one of the biggest reasons. Well, there's actually two. From my perspective, the measurements have been lacking because they're very, very challenging to make. But until we have really, really accurate measurements, we're not going to have really accurate models. And so we've been focusing on the measurement component, keeping in mind what the models are actually doing. So the models, because they're so large and require lots of computing power, also because, as I say, the measurements haven't been there to change it, present a relatively simplistic picture of aerosol chemistry. Sulfate aerosol is sort of one of the types of aerosols that get sort of bandied around. There are other modelers that are developing more and more sophisticated models, but those have not achieved sort of the global scale that yet. But I think they will get there. As I say, they have to have the proper inputs, though. The chemistry is overall quite complex, and it, as opposed to CO2 and other greenhouse gases, it's highly variable. It depends on where you are. Because of aerosols, you can have warming in certain parts of the world, and in another part you could actually have cooling. And so you're looking sort of at these large gradients due to the aerosols. And basically, there's really not much known about sort of the chemistry that happens and how that changes the properties. These are all the different processes that could happen or do happen. Very few of these are included in models, or there's major assumptions made if they are for the large part. But this is the direction that modelers are moving. They're trying to go in and do fundamental studies to understand a lot of these processes by looking at sort of stepping back and looking at the individual processes themselves. The questions that we had when we started out are, if we can measure things in real time, if we can measure things fast, if we can measure chemistry well, can we actually measure the climate impacts of real aerosols out in the real world? And that was debatable when we got started. Can we measure how atmospheric particles evolve, and in turn how those particles impact climate? And then climate actually will turn around and change due to those changes and can turn around and impact the particles. So there's this dynamic interaction between the two systems that is very, very difficult to unravel. How do these changes, as I say, impact the properties that ultimately impact climate? And the two areas that I'm going to focus on are measurements of optical properties and cloud formation that we've been doing recently. So stepping back, what's the way we have looked at aerosols? For years, it's been basically pulling air through a piece of filter paper, collecting bulk samples, and then trying to sort of understand what the aerosols are composed of. And basically, we have to assume an average composition, that all particles in the atmosphere look the same. And that is, or if we want to get fancy, we have to assume what is the mixing state? How were these species originally really split up? And there's a lot of assumptions involved in that. Our approach has been to look at single particles. By doing that, we can get separate fingerprints for each particle and link that back to the sources. We can also say how much a particle has actually undergone aging in the atmosphere. In turn, how these different types of particles impact health and cloud formation and optical properties. So we've been trying to sort of reduce it down to a very simple form, looking at one particle at a time. The method that we developed when I first became a professor, and we've been using as well as a wide variety, I should point out there's a lot of different measurements in a lot of different groups doing this type of research. And basically, you need as many approaches as you possibly can get. Intercomparisons are critical, especially when you're making sort of newfangled measurements that you're not really sure what you're going to see. But basically, it's a real-time instrument that pulls particles into the system. We scatter light off of the particles. I should mention my training was in molecular beams, and so this is sort of a boiled-down version, but now instead of looking at the gases, we're looking at the particles. So the particles come in, they undergo a supersonic expansion, they pick up different velocities depending on their size. So we can track each particle by measuring the speed between two scattering lasers. That gives us the size of the particle, so this is the particle sizing region. We now know the position of the particle, the speed of the particle. The smaller particles move faster, bigger particles move slower, so we can equate that with size. And we can basically determine when it's going to get to the center of our chemical analyzer, which is a dual polarity time of flight mass spectrometer. So it's essentially two mass specs, where we do laser desorption ionization. We blow each particle apart using a pulse laser into bits and pieces and detect positive ions down one flight tube, negative ions down another tube. It's really important to get as much information on each of these particles as you can. You only get one shot at them. But what we're able to get is size, how chemistry changes as a function of size, and most recently, I'll touch on this a little bit, we can look at the optical properties. We're linking this chemistry, hopefully, ideally with specific sources where it came from, and we're starting to bridge it with the climate parameters. So stepping back to the filter method, what you basically get, these are the basic components of aerosols: organic carbon, soot, sulfate, nitrate, ammonium, and dust. And you measure a total mass. and you look at how it's divided between the different chemical species. And from this, you try to sort of figure out where things came from, which is a bit challenging. This next slide is overwhelming, sort of, but it's just, I'm going to sort of go through and explain. This is our perspective, which is basically, instead of looking at individual species, we break things down as a function of size and the percentage of them in the atmosphere. So we can just count them up and figure out where the major sources are coming from. We can link that with a source or chemistry. You see there's a very strong size dependence, mostly carbonaceous, fossil fuel combustion, biomass burning, fall below a micron, whereas dust and salt, sea salt in particular, fall in the larger sizes. These are actually microbes from the ocean that we see in marine environments. And then we look at where are the reaction products going. In other words, where's the organic carbon, ammonium, sulfate, nitrate, which form by atmospheric reactions, where are those going? So having these aerosols present in the atmosphere completely changes the chemistry of the trace gases. Without the aerosols, there's modeling studies that show a completely different atmosphere if they weren't there. They present a huge surface area, very similar to what people discovered in the stratosphere with polar stratospheric clouds. They induce reactions to happen that just wouldn't happen if they weren't present. So the two examples I want to focus on, impact of soot on climate. This is just to show you the spatial variability, this is a model that's been constrained by measurements by one of my colleagues, Professor Ramanathan down at Scripps and Greg Carmichael at Iowa. And basically what it shows you is what I've been saying is that the warming that you get from, and this is just focusing on soot, comes mostly from, or comes over land, and you see a very large gradient in the temperature depending on where you are. And basically, Professor Ramanathan has come up with a really nice way of actually measuring, direct measurements, not modeling, direct measurements of heating rate, flying UAVs through the atmosphere. And so they used a lot of those measurements to sort of constrain models and come up with this map. And what they found was the IPCC estimates that the forcing due to, the forcing due to, or the warming due to soot is about 0.4 watts per meter squared, which makes it very strong forcing agent, equivalent to, or second only basically to CO2. Professor Ramanathan's work puts it at about 0.9. Other measurements, depending on sort of what your assumptions that you make, put it up closer to 1.2. Very strong forcing, warming, where a lot of people always say, think of aerosols as cooling. And so the question is, why is there this range? Is there a way we can explain it from direct measurements of the soot that's present in the atmosphere? This has large implications for, as I mentioned, regional weather patterns as well as other aspects of climate. So one of the things that we are interested in is, can we go in and look at the soot and see sort of how it's mixed, and can we sort of use our measurements to further sort of come up with a link with the measurements that are made on the heating rate by Professor Ramanathan. And so basically, we've looked at sort of the optical properties of the soot specifically. Only recently we added that ability. One of the questions is, a lot of people look at sort of how fast does it transform in the atmosphere, because soot will change. As it changes, the optical properties change. Also, the cloud forming properties change. So can we pick that out using real-time measurements? And then how do these impact the optical properties? So thinking about things from a mixing state perspective, if you think about sort of, this is a very hypothetical scenario, where you have 90% soot you've measured on your piece of filter paper, 10% sulfate, you have two scenarios. You can have every particle looks the same, which is basically what you have to assume, or you can have basically sulfate, which is very reflective and cooling, and mostly soot, which is warming. These two scenarios have very different optical properties and also warming potential. The bottom line, when I first saw this, I used to think, okay, if you put sulfate on the outside of a soot particle, maybe you're going to reflect all the light back to space, and this will be good because you'll shield the warming part, the absorbing part. But what actually happens is you put a material that's got a high refractive index on the outside of these particles as they age, it actually causes a focusing, so you get more warming. So now you've taken your friend, sulfate, which is everybody loves to think of as cooling, and you've made it become an actual sort of accessory to the crime, and it starts to cause extra warming by up to a factor of 3. for soot. So this can start to close the gap. The range that you get for the forcing of soot in sulfate now can start to make a little more sense if we can look at this a little more closely. So a bit of data. This is single particle spectra from a single soot particle. We call it soot because it has a very obvious carbon pattern. This is an electron microscope image. Fresh soot is very fractal aggregates of little carbon spherules that are combined together. And as it ages, you get a picture more like this. As soon as you start to put down species that like water, the particles start to absorb water, and that fractal geometry collapses. And those have completely different optical properties. So the question is, what we're interested in is, how are the can we see a difference in the optical properties of these particles versus these particles? And so this is just a bit busy, but basically it's the scattering or optical properties of different types of soot, where we've taken basically each one of these points represents the optical properties of a single soot particle. And what we found was the fresh soot, for smaller sizes, scatters much more, as you would expect for a large fractal type particle. But as time goes on and the particles age, they start to scatter less and less and grow in size, and it collapses into this is the me theory curve. It's basically what can describe the particle based on its shape. And so, in fact, we do see this transformation in the atmosphere. And the question is, how fast does it happen? So this is a time series. We see the same thing in Mexico City or Riverside, which are photochemical environments. Time of day versus the amount of soot. And you see there, the blue is the fresh, this is supposed to be relabeled, sorry, this is fresh soot. And then the red is the age. So it's color-coded to go with this. And basically, the answer is it happens very quickly. You don't have that much fresh fractal soot for very long, unless you're in the center of an urban city where the soot is being emitted. We can look at this for measurements we've made all over the world, and we've basically gone in and said, okay, how often do we see the fresh soot signature? How often do we see the aged or the mixed soot signature? And the take-home from this is that it's safe for modelers to basically go in and realize that it's either sulfate or nitrate, or organic carbon, and also water, that are condensed on these soot particles. And so from a modeling perspective, this is actually really important. We can quit switching back and forth what if. I think we are pretty confident that fresh fractal soot does not stick around for very long. Similarly, fresh sulfate doesn't stick around for very long. They combine very quickly in the atmosphere. So switching to dust, these are just events just from this year. Dust is the largest aerosol worldwide. It's present globally, and you can see it from space. This, as I mentioned, is a huge surface for reactions to happen upon, and being a chemist, that's why I like it. It is rather messy. We actually did some studies, or a study on Jeju Island in Korea. This is during a dust event. People put on the masks very quickly. So let's step back and think about just dust reacting in the atmosphere. This is the part that basically the understanding is relatively poor. If we take two different minerals, aluminosilicates are one type, calcium carbonate's another type, we think about secondary species that might mix on those particles. We take these two particles, we put them into this mix. I made this movie myself. You can tell, I know. But anyway, my students were shocked. But anyway, so basically what you see is here's the core of each particle. And the question is, does each particle sort of react the same? And this is almost embarrassing as a chemist to ask this question, but believe me, dust in models is treated the same. There's one entity in the atmosphere, it's called dust. It has one rate constant with whatever species you're talking about. So all dust evidently reacts the same. So anyway, so we were humoring that sort of view and saying, okay, is this true? Or in fact, do you see different reactivities depending on the chemistry of the core? And so basically these two scenarios right now, this is more the treatment that the sort of the way you look at it in models. We actually were wondering if we would see something like this. And so basically it's really important to do this because this is what we assume. And it's sort of like your standard sort of bimodal, exam scores, where you've got students that got 10s and some students that got 90s, and you say your average is, the students knew about half the material. Turns out none of the students knew half of the material. Same thing here, where basically the properties, the climate relevant properties that you care the most about, you'd completely mispredict from the standard picture where everything sort of reacts the same. Whereas in fact what we do see, as I'll show you in a second, is we see mineralogy plays a huge role. And so basically, to do that, we've had to go into the field. We've went in a variety of platforms. We've been on ships. We've most recently done airplanes. We've got a mobile lab. This is really interesting transport. We aren't doing measurements while they're carrying it. But this was actually in India, where there aren't any sort of ways to move our big instruments around. So this is a mass spectrum of a single dust particle in the atmosphere. And you can see the typical mineralogy. This is an image. And then in the negative ions, this is where you can see we can look at the degree of reactivity. We can look at those secondary species and watch them come and go and study how these products change as a function of the minerals that are present. And so when this is a messy one, but I'll try and walk you through it. This is looking at single particles with different amounts. If they have 100% calcium as the mineral, it's up in this corner, 100% aluminum down here, 100% iron down here. Same thing on this side. So it's the same particles, looking at the amount of sulfate and nitrate on these particles. And so basically, these are the two classes that I'd mentioned before. And what you see, hopefully, is that the sulfate content on these particles is quite low, whereas the nitrate on those same particles is very high, and vice versa. Here we have lots of sulfate, very low nitrate. So we're seeing completely different partitioning of the species depending on the mineralogy. And this was the very first measurements that actually showed this. There were some lab studies that basically said this could happen. These are the first field studies that actually showed, in fact, that mineralogy plays a major role. And from a fertilization perspective, everything else has major ramifications. Again, so sort of looking at things, stepping back. So we did the field study, we saw the dust, we learned a lot, but we had a lot more questions than answers. So we went back to the lab, and what we can do is we can actually simulate clouds in the lab. We can vary supersaturation ratios, which mimic those that would be in a cloud. So we're changing the RH, basically, above 100%. And we can look at the fraction of particles that activate as a function of supersaturation. So we can start out with a simple mineral like calcium carbonate, and basically we're ramping up the supersaturation. All of a sudden we hit here, and this is activation. The particle starts to grow and turns into a cloud drop. What you see is, for calcium carbonate, that happens at a relatively high supersaturation. We can take these calcium carbonate particles, react them with nitric acid for various differences in time, march it down to calcium nitrate, which is very hygroscopic, and what we see is the supersaturation for this to convert to a cloud drop changes. It gets much lower supersaturations, which says that the reactions are actually changing the cloud formation potential of these particles. This is lab studies, but we can take the kinetics from these types of reactions. I won't go into a huge amount of detail, but we can calculate an atmospheric lifetime, how long it takes the calcium carbonate to convert from not a very good cloud particle to something that is very good. It takes less than an hour. And you can do this for various nitric acid concentrations. And this is consistent. In the atmosphere, when we measure calcium nitrate particles, they're not big old morphologically sort of distorted particles. They're actually nice spheres that we can model with me theory. So the consistency between the lab and field studies is actually quite nice. But the thing about the ground-based studies is you can learn which parameters are important in forming clouds, which particle types are better, which particle types are worse. So it tells you about the things that are important in forming clouds, but you're missing sort of what does form a cloud. So to answer that, we did a series of flights in November of this past year, and the question is, how different is the aerosol that's feeding outside of the clouds into the clouds? Do we see any sorts of enhancements in the particles that are outside versus inside? Is chemistry playing a role? Which for a long time, and a lot of people, and I'll mention this again, believe that size is really all that matters. So here's the setup. We sampled from what's called a counterflow virtual impactor, which is a fancy way of saying we only let the big droplets and ice crystals pass. So we weren't looking at the aerosol inside the clouds. We could switch back and forth. But the goal here is to look at what really were forming the clouds. And so we could evaporate those down and then measure their size and chemistry in real time. And so basically, when we were doing these flights, we were looking at different, we can look at where the air masses were coming from. And they are always coming, for the most part, from these directions. I'm going to talk about RFO1 and RFO3 here, but basically they're coming from pretty similar regions. And so, as I mentioned, we're looking for an enhancement due to chemistry. The big question is there any difference in the chemistry of ice versus liquid clouds? And that has never been addressed before because ice are very difficult to measure. Their concentrations are so low that if you try to catch one and then go look at it, it's really, really challenging. But we only need one particle at a time, so we're able to actually differentiate between those two phases. The big question, these are sort of some of the battles that have been going on in the literature. Andy Andrea came out with size matters more, the big grand statement. How do aerosols affect precipitation? These are some of the questions. And so these are sort of the things that we're thinking about. One of the types, sort of punchline of the whole thing, that we saw repeatedly were these very specific types of dust. Positive ions, we would see, they look a lot like sea salt, but they're not sea salt. They're actually enriched in what we would call hygroscopic or very soluble salts. In the positive ions, and the negative ions, they have markers actually indicative of biogenic material. So they were looking a lot like dust, but with a lot, or dust-like particles, but they're very, very salty. And so the question is, where did those particles? I'll come back to that. So this is again a messy one, but I think I'll walk you through it. So this is this is flying through a cloud, and we're switching back and forth between out of cloud and in cloud, looking at cloud drops. So everywhere there's a green marker, this is sampling from the CVI. So what you see is out of cloud is the sort of reddish, all these other different colors. Every time we switch to the CVI, these salts dominate. They completely dominate. And so this was a surprise. This wasn't, people have seen sea salt as being important. A lot of people think ammonium sulfate should be important, but these salts were not really anticipated. So we looked at the origin of the air mass a little more closely, and every time this happened, the air mass was coming right over the Great Salt Lake region. So we believe these are the dry salt lake beds. And if you think about how a dry salt lake dries out, it's sort of like Mother Nature's made the perfect cloud seed. Because as the lake bed dries out, the most soluble, and Tony Wexler's written a paper about this, the most soluble material will end up on the very top. And so when you have a windstorm, it picks off the very soluble material, the best cloud seeds you can possibly get, and lifts those into the atmosphere. And a lot of people hadn't really thought about this, because most people, when they're trying to understand the potential impacts of these, go scoop the dirt out of the ground and look at everything. They're missing the stuff that gets levitated. So the take-home in this for us is that size is important, no question, but in this case, the chemistry was playing a major role. Just the amount it dominated was a big surprise to us. So conclusions, basically we are working very hard to sort of provide a more accurate picture of the mixing state of aerosols, to sort of be able to really say how they're affecting climate and how things will turn out over time, hopefully. The flight experiments were very enlightening, because they really showed us that it's really important to go back and forth and to actually do the flights and see what's really up there. I mentioned that we're using both of these. We're really working hard with modelers. They say our data are finally useful. There was a pretty big disconnect between what we were measuring and what modelers needed. And so we communicate very differently. And so now we're starting to bridge that gap, and I think that's a really exciting thing to be doing. One thing I want to point out is Jim had mentioned things we might be able to do, and a lot of people talk about this sort of geoengineering approach. Paul Crutzen, I talked to him, and he said he was just sort of joking when he put that out there as an idea for people to ponder. We never know what we're going to have to do if things get really bad, and it might be good to have some special bags of tricks in our back pocket if we need them. But basically, I feel very nervous knowing how little we know about the aerosols, at least from the aerosol perspective, making any major changes. People really honestly say, put more sulfate up, or remove this, or whatever. If we don't know things better than we do now, I'd be really nervous about that. And so I think we really need to push very hard in the little window of time that we might or might not have to understand these things better. And one of the ways we look at these particles is that they're actually, in a way, they're very short-lived. So any change we make will be relatively rapid compared to CO2. And so it's a way that maybe we can think about buying some time while we sort of grapple with what the best other approaches are. But anything we change, it will be a relatively quick change, and maybe it will ease some of the strain that our planet is under right now. And as I say, I don't really love the idea of geoengineering, but at the same time, I think it's smart. Jim pointed it out. It's very true. We're already messing with the system. So to say that, oh, don't touch it, we're already doing that. I think we need to understand how what we're doing right now really affects what's going on. So I'd like to acknowledge again the Camille and Henry Dreyfus Foundation for the invitation. My entire group has just been fantastic. They are just, I wouldn't be standing standing here if it weren't for them. I've established the last few years, since we've been doing the cloud work, a wonderful sort of collaboration with Professor Kreidenweiss and Paul DeMont looking at ice, and Marcus Petters at Colorado State. And the funding sources for the work that I've described are from NSF. And I always finish my talks up with just keeping in mind that every little thing that each one of us does can be amplified. And this is my son looking at a tide pool, which we know has changed already in our lifetime, and I would like to play a role in keeping that tide pool at least somewhat there for his future, for his children. So anyway, with that, I'd like to thank you for your attention.
Thank you, Kim. Exactly on time.
Oh, wow, I was talking fast.
We have time for a few questions. Please identify yourself and use the microphones.
So, Alan Stone from Johns Hopkins. You mentioned that today we have 60% of the Earth's coverage by clouds.
On average, yeah.
What was it like 200 or 400 years ago? Does anyone have any kind of idea? Before we had jet planes and so many smokestacks?
Yeah, that's a good question. I mean, obviously there were clouds. I don't know what the percentage. Do you know what the percentage? I mean, I don't know if it was how much different the cloud coverage was. Yeah, I'm asking you. Do you know? Because I actually don't know.
Yeah, this is pre-industrial. We have extremely good records from Asia, from Europe.
For cloud cover. For cloud cover. I don't think. Do we for cloud cover? I don't think.
Yeah, the albedo of the Earth.
No. I'm just thinking of the clouds themselves. For the albedo, yeah, but I'm saying I think he was asking if we had clouds.
Yeah, it hasn't changed dramatically. We have the evidence from pre-1750.
Right.
So it's obviously an issue. The cloud creation is now with smaller particles. The cloud's little.
We're changing the droplet size.
And
yeah.
you can see from the forcing there that it's a 0.6 of a watt per square meter thereabouts.
Right. Sort of, yeah.
But that's basically the structure.
Mm-hmm. I mean, we know we're also modifying the clouds, not just the number that are there, but we're changing the droplet size and all the other parameters of the clouds. But yeah, anyway.
Yes, Kim. Don Stedman, University of Denver. I and Dreyfus, I'm sure, would be happy that you said the chemistry matters. You also said the regulators are happy if your science tells them how to regulate. My experience of the last 20 years is that's not always correct.
It's not always correct. I'm being optimistic on that statement. But yeah, I mean, I would say they're more, over the time I've been doing this, I would say they've become, maybe I'm just talking to the right people, but they seem more inclined. I've learned which things to say to them where they just sort of glaze over versus which things they act like they're going to go do. And they have made changes, So I just know that certain answers we give them aren't going to budge them. And certain answers, certain directions we can go, we can sort of move things along. I do see a difference. And I have seen it change over time, so.
Question before break? Last question. Oh.
Charles Dismukes, Princeton. You mentioned the case of biomass and comparing that with regards to carbon-based or soot-based particles. As we go forward from here, of course, we're going to have a bigger fraction of that contributing. And sources could include such things as terrestrial biomass, but also lots of people are thinking of using marine-based biomass. And so I presume there will be a difference based upon what you just said about salts, marine salts. So could you sort of predict what would be worse of these two scenarios? And I'm not sure if they're doing pyrolysis or gasification.
Yeah, the biomass that I was referring to was pyrolysis. So it's like biomass burning, combustion. So, and I mean, sort of that's being, in a sense, that's changing also, especially in the western United States, because we're just getting far more, as things are drying, we're getting far more wildfires, and we're sort of in the middle of a pretty vicious cycle. But as far as, biomass burning is sort of the number, if you ask me globally, what's the most important sort of source that I see everywhere I go? To varying extents, biomass burning is a big one for a variety of reasons. In the poor countries, people are burning very ineffectively, burning very poor heat sources and cooking sources. And so there's a lot of reasons, a lot of different that's a catch-all for a lot of different sources. And it's all intertwined. And I think to sort of sort out the fractions and the overall impact, we're a ways away from doing that, unfortunately.
One more question.
Peter Stang, University of Utah. I don't have a question. I'll offer a comment, and that is those of you who are skiers know that Colorado and Utah has the best skiing, has fluffy powder snow. Our water content is something like an inch of water per 16 inches of snow rather than the usual 3.5. And the hypothesis is that this is due to what you mentioned, and that is picking up the salt crystals from the salt flat that then act as seeds.
Is that actually published? Because we talked to people about it, and they are sort of in denial, as far as that it sounds like the skiers have got it figured out, so maybe I better...
Heather Allen, Ohio State. I noticed that the potassium was the largest signal. Can you comment on that? And is that similar than what it would be over the ocean, or is it the dry bed?
Potassium I'm trying to remember which figure.
When you talked about the trajectory and the
in that salts. Okay, yeah. So potassium can be the largest signal, but it doesn't have to be the most abundant ion. Right, you have different sensitivities to different species.
So when it's normalized, then for that,
it would be less than the magnesium and calcium salts are the really abundant ones. Yeah, thank you for pointing that out. We have a very high sensitivity, so you have to normalize to your sensitivity factors.
Thank you again.